Hello friends, welcome to engineering tutorial. So in the previous video we discussed about the time response analysis of zero order system. Okay, so in this video we are going to discuss about the first order system, some basic concepts related to that, and then the time response analysis of a first order system to various inputs such as step, ramp and impulse input. So we know that a basic layout of a control system, it consists of a forward path block, okay, it is the output. Then we have the feedback block, okay, here is the summer, it's a negative feedback that is normally used, and this is the input. Okay, so this is the basic layout of a control system. Now in a first order system, now if we refer to the definition of the order of a system, it is the highest power of S, okay, the highest power of S in the denominator or the characteristic equation or denominator of closed loop transfer function. Okay, it is the highest power of S in the denominator, which is the characteristic equation of the whole system in the closed loop transfer function. So the order is determined from the closed loop transfer function, the denominator, and the type from the open loop transfer function. Okay, the number of poles at origin, that is type. And order, it is the highest power of S in the characteristic equation or the denominator of the closed loop transfer function. So now we will see how we can design a first order system from this. Okay, so now we will make some changes in this layout and we'll put certain values in place of GS and HS to design a first order system. Suppose we put GS, the forward path gain, as 1 by S tau, and we have a unity feedback, okay, unity negative feedback, that is HS is equal to 1. Suppose we make these changes here, so let's see what happens. So here 1 by S tau, this is the forward path gain, and here it is unity feedback, okay, that is the gain is equal to 1, the feedback path gain is equal to 1. So here the open loop transfer function, the open loop transfer function, remember GSHS is equal to 1 by S tau, okay, but the closed loop transfer function, the closed loop, this is the open loop transfer function, but the closed loop transfer function, that is equal to the closed loop transfer function, that is GS by 1 1 plus GS HS. So that will be 1 by S tau, which is GS, by 1 plus 1 by S tau. So that will be equal to 1 by S tau by 1 plus S tau by S tau. Okay, so here S tau and S tau will get cancelled out. So the closed loop transfer function, that will be 1 by 1 plus S tau. This is the closed loop transfer function, 1 by 1 plus S tau, and this is the denominator, which is the characteristic equation. The denominator of the closed loop transfer function is the characteristic equation. Now see, the highest power of S in the denominator or the characteristic equation in the closed loop transfer function, here the highest power of S is 1. Okay, it is 1, so it is a first order system. Okay, this is a first order system. So we have designed a simple first order system. Now we will use this to find out the output response for various inputs, such as step input, impulse input, ramp input, and we'll study the output waveform with respect to time. Okay, so just now we designed a simple first order system, and the transfer function, the closed loop transfer function of that system we found out, and it was CS by RS, the closed loop transfer function. It was 1 by 1 plus S tau. Okay, now we can also represent this as, if we divide tau in both the numerator and the denominator, here it will be 1 by tau by 1 plus S tau by tau. It will become 1 by tau by S plus 1 by tau. So this is one way of representing the transfer function, and this is one way of representing. This is normally called the time constant method of representation, which is generally used in board plots, okay, to find out the corner frequencies and all that. And in all other analysis, you will generally find this way of representation of transfer function. So both of them are valid, both of them are correct. So it depends for what purpose you are using and what is your style of representation. So you are free to represent the transfer function in whichever form you want. Okay, so this is the closed loop transfer function. Now we will study the output response, that is the behavior of CS when the input is unit step. So I have already discussed about the various inputs, okay, that are given to the systems to study their output response. So the unit step input, it looks something like this. I've already told you. So it has a constant value which is equal to 1, and it exists for positive values of time. For t greater than equal to 0, its value is equal to 1, and for t lesser than 0, its value is 0. Okay, so and the Laplace transform of the unit step input, the Laplace transform of unit step input is equal to 1 by s, because it has a value of 1 and Laplace transform of 1 is 1 by s. Okay, so this is very important to remember. The Laplace transform of unit step input is 1 by s because we will be using the s domain approach. So this is very important to remember. Okay, so the input is unit step, and we'll study the time response of the first order system to unit step input. Okay, so Cs by Rs is equal to 1 by 1 plus s tau. This is the output in s domain, this is the input in s domain. Now just now we found out that the Laplace transform of unit step input is 1 by s. Input is unit step, so Rs is equal to 1 by s. So Cs here equal to 1 by 1 plus s tau into Rs. 1 by 1 plus s tau into Rs, which is equal to 1 by s. Okay, okay. Now it will be suitable for us if we convert this time constant representation of transfer function into the other form. Okay, so we will multiply 1 by tau in both numerator and denominator. Okay, so it will become s plus 1 by tau into s. Okay, this function, it got converted into this. We just multiplied 1 by tau in both numerator and denominator. Okay, now we can write this numerator as s plus 1 by tau minus s. Okay, what we did is that we represented this numerator in terms of the terms present in the denominator. Okay, we express the numerator by manipulating the terms present in the denominator so that it will be very easy to factorize them. See, s plus 1 by 2 minus s is 1 by tau, and this is s plus 1 by tau into s. Okay, again I am writing it in this side, so it can again be written as s plus 1 by tau by s into s plus 1 by tau minus s by s into s plus 1 by tau. Okay, this can be written in this way. Now s plus 1 by tau, s plus 1 by tau got cancelled from both the numerator and denominator. Here s and s got cancelled out. Okay, so here it is 1 by s, and here it is minus 1 by s plus 1 by tau. This is Cs, this is Cs. So we got Cs. The value of Cs we got. Now we have to convert it into time domain. Now what we will do, we will take the inverse Laplace transform of Cs. Okay, the inverse Laplace transform of Cs will give us the time domain signal, the time domain representation. Okay, so we'll do it. So we just determined the S domain of the output, and we found out that it was in the form of 1 by S minus 1 by S plus 1 by tau. Okay, so now we will take the inverse Laplace transform of CS. So the inverse Laplace transform of CS, it is equal to Laplace inverse of 1 by S minus Laplace inverse of 1 by S plus 1 by tau. Now we know that the Laplace transform of 1 is 1 by S. So the Laplace inverse of 1 by S will be equal to 1. Also, we know that the Laplace transform of e to the power minus at, Laplace transform of e to the power minus at, exponential signal where a is any constant, is equal to 1 by S plus a. So here you pay attention, if we substitute a with 1 by tau, okay, if we substitute a with 1 by tau, so Laplace inverse of 1 by S plus 1 by tau will be e to the power minus t by tau. Okay, so these are the formulas that we are using. Okay, so Laplace inverse of 1 by S will be 1 minus, here it will be using this formula, it would be 1 minus e to the power minus t by tau. This is equal to Ct, the time domain representation of the output. Okay, 1 minus e to the power minus t by tau. Okay, so we found out the time domain representation of the output for a first order system to unit step input. This is the S domain version, this is the time domain version. Okay, so we just found out the time domain representation of a first order system output to unit step input. So if you look closely to this output equation, you can find out that it closely resembles the charging equation. Okay, the charging equation in RL and RC circuits that we come across in transient analysis. Okay, transient analysis. Okay, so now let us study the behavior of this output response at various time. At t equals to 0, okay, at t equals to 0, C0 will be 1 minus e to the power minus 0 by tau, which will be equal to 1 minus 1, which will be equal to 0. At t equals to infinity, means steady state, it will be 1 minus e to the power minus infinity by tau, which will be 1 minus 1 by infinity, which will be equal to 1 minus 0, which will be equal to 1. So this is the steady state value, the steady state value. So if we try to plot this, okay, if we try to plot the output response of the first order system, it will look something like this. Okay, this is the axis. Okay, this is CT 0. So it will look something like this. Okay, at steady state it is equal to 1. Okay, so this is the output response of a first order system to unit step input. Another interesting thing to notice here is that what will happen at t equals to tau. Okay, at t equals to tau, it will be 1 minus e to the power minus tau by tau be equal to 1 minus e to the power minus 1. So e to the power minus 1 is generally 1 minus 0.368 approximately. So it will be equal to 0.632. Okay, so this is the time constant. Okay, so at tau, the value, it will be 0.632. Okay, the value will be 0.632, and at steady state it will be, the value will be 1. Now the steady state, it normally occurs at time interval, after a time interval 4 times of the time constant. So after that is the steady state occurs, and before it everything is the transient state. Okay, and after that everything falls under the steady state analysis. So this is the output response of a first order system. Okay, the first order system to unit step input. Okay, which is a charging equation which we come across in RL and RC transient analysis. Okay, so I hope you like this video, and please subscribe my channel Engineering Tutorial for more such videos related to electrical, electronics, instrumentation and communication engineering. Have a great day. Thank you very much.